Welcome back. In this video, we are going to solve exercises 1 to 4 of chapter 5. Exercise 1, we equip R with the distance rho given by x cubed minus y cubed. We know that this is a distance. We have to show that R rho is complete. Second question, we equip R with another distance, rho 1, which is given by ex minus ey in absolute value. And we have to show that R is not complete for rho 1. So we have to use two distinct strategies. To show that R rho is complete, we have to start with an arbitrary Cauchy sequence and prove that it is convergent for this distance. In the second question, we have to find one Cauchy sequence which is not convergent. Okay, so don't confuse these two ideas. So first question, let Xn be an arbitrary Cauchy sequence of R rho. This means, if you go back to the definition, that for every epsilon positive, starting from a certain rank, the distance with respect to rho between two terms of the sequence is less than epsilon, or which is equivalent to, if you replace rho by its value, it's equivalent to saying that xn cubed minus xm cubed is less than epsilon starting from a certain rank. So this means that actually the sequence xn cubed is a Cauchy sequence in R equipped with the usual distance that we call d. This is a different distance than rho. But R with the usual distance is complete. Therefore, xn cubed converges to some limit x in Rd, okay? Which means that the usual distance between xn cubed and x, or xn cubed minus x, if you like, can be made arbitrarily small for all n large enough. Now, if we set y equal to x to the power 1/3, then rho of xn and y is simply xn cubed minus y cubed. And this is just xn cubed minus x. And this tends to 0, or can be made arbitrarily small as n goes to infinity. Therefore, this means that xn converges to y in R rho, and therefore R rho is complete, since the sequence was arbitrary. Okay, second question. As you said, you have to find one Cauchy sequence in R rho 1 which is not convergent. Okay, how to think of this? What do we want to prove? We want to find a sequence xn of real numbers such that exn minus exm tends to 0 as nm become very large. But however, we want exn to not converge to any ex, so does not converge to any positive number. Now this is easy. It's enough to take any sequence converging to minus infinity, then these terms go to 0, but then in this case exn goes to 0, so cannot be equal to ex. This is the idea. So more formally, we can just choose xn equal minus n, but this is not the unique choice. You can write minus n squared or minus radical n. It will work as well. So more precisely, if we take xn to be minus n, then rho 1 of xn xm is by definition e to the minus xn, or e to the minus n, minus e to the minus m. And this, of course, tends to 0 because the exponential tends to 0 at minus infinity. So this means that xn is a Cauchy sequence for rho 1. And as you observe, xn cannot converge to any element x for rho 1. So, by contradiction, suppose that xn converges to some x in R rho 1, then rho 1 of xn and x will be exactly the absolute value of e to the minus n minus ex. So if xn converges to x for rho 1, then this quantity would converge to 0 in the usual sense. So therefore, e minus n converges to ex, but e minus n converges to 0. Therefore, by uniqueness of limits, we must have ex equals 0, and this is impossible. So this means that xn is not convergent in R rho 1. And therefore, R rho 1 is not complete. So this concludes exercise 1. Exercise 2. we consider the space of continuous functions f from the closed interval ab into R, and we equip it with the maximum distance or the supremum distance that we mentioned in chapter 1. We know that this is the distance. We have to show that CAB equipped with this distance is complete. So we use the same strategy as in exercise 1. We start with an arbitrary Cauchy sequence, Fn. So this is a sequence of functions. This is a sequence of continuous functions, okay? Not a sequence of numbers. And you have to show that Fn converges to some element, some limit f in CAB. So let us write the Cauchy condition. For every epsilon positive, there exists a certain rank starting from which the supremum, or the maximum in this case, because we know that this is a maximum, because a continuous function on a compact set achieves its supremum. So the supremum of Fn of x minus Fm of x is less than epsilon, or equivalently, for every epsilon positive, there exists a certain rank starting from which Fn of x minus Fm of x is less than epsilon for every x in AB. And so we can label this condition as, so we can say that Fn is a uniform Cauchy sequence because the n0 depends only on epsilon and not on x. So we call this condition E. Okay. So in particular, if we fix x, the sequence of real numbers Fn of x is a Cauchy sequence in R with the usual distance. But R with the usual distance is complete. Therefore, Fn of x converges in the usual sense to some limit f of x. The limit depends on x. So this defines a function. So for each x, I have a limit. Therefore, now I have a function f from the closed interval ab into R. So now we have to prove 2 points. First, that f is continuous. And second point, Fn converges to f in CAB. And you already observed, perhaps, that convergence in CAB is equivalent to uniform convergence. Okay? Because it means that the supremum is less than epsilon. Okay, so now fix epsilon n0, n and m, n, sorry. So fix epsilon n0, n and x, and let m tend to infinity. What happens if in this condition we let m tend to infinity? If m of x converges to f of x. So at the limit, inequalities are conserved, but they become large inequalities. Okay, so when we let m tend to infinity, in this inequality, we get Fn of x minus f of x is less or equal than epsilon. Okay. So we have proved, since epsilon, n, and x were arbitrary, so for every epsilon 0, for every epsilon positive, there exists a certain rank starting from which Fn of x minus f of x is less or equal than epsilon for all x in AB. Okay. So actually, if you studied calculus before, this precisely means that Fn converges uniformly to f of x. Okay. So, and you probably know that if a sequence of continuous functions converges uniformly, then the limit must be continuous. Okay, we shall reprove that. Okay, we want to prove that f is continuous at every point, x0. So pick x0 in AB and let x be another point, and let epsilon be given. And choose n0 as in this condition, depending on epsilon. We want to prove that f of x minus f of x0 can be made arbitrarily small if x is sufficiently close to x0. So for this, we use a standard argument. We use the triangle inequality. So we add and subtract fn0 of x and fn0 of x0. So this is the triangle inequality. Now, by condition f, the first term is less than or equal than epsilon. And the third term as well, because this is true for every x. Okay. Now, what about the second term? Fn0 is continuous. Therefore, at x0. Therefore, there exists delta such that the second term is less than epsilon if x minus x0 is less than delta. Therefore, we have proved that if x minus x0 is less than delta, then f of x minus f of x0 is less than 3 epsilon. Okay. Now, 3 epsilon, 100 epsilon, same thing because epsilon was arbitrary. So this proves that f is continuous. at x0, and since x0 was arbitrary, this means that f is continuous at every point of AB. So f belongs to the space CAB. So this is the first point. And now the next point is already proved here, actually, because if you look at this condition f, you can be written as for every epsilon positive there exists N0, starting from which the supremum of fn of x minus f of x is less or equal than epsilon. So this means that the distance between fn and f is less or equal than epsilon. Okay? So this precisely means that fn converges to f in the space CAB equipped to this distance. Okay? So this is just uniform convergence. This is a standard result. So this concludes exercise 2. Exercise 3, about the Banach fixed point theorem. We equip R2 with the distance ρ1 of xy, x prime, y prime as being the distance between the first two components plus the distance between the second two components. Okay. Of course, we could have taken the Euclidean distance or the maximum distance, doesn't really matter, but this is somehow convenient. So we consider the vector field from R2 to R2 given by these equations. So f is a function of two variables, x and y, two real variables, and has two components. The first component is 2 over 5 sine x plus 1 over 5 cosine y. The second component is 1 over 5 cosine x plus 3 over 5 sine y. We have to show that f is a contraction and then deduce that this system, this nonlinear system of two equations and two unknowns, has a unique solution x, y, and r. Okay, so we go back to the definition, but we have to use this observation that sine t minus sine s and as well as cosine t minus cosine s are both in absolute value less than t minus s. Of course, you can prove these standard inequalities by using trigonometric formulae, but the easiest thing to do is to use the mean value theorem, because the derivative of sine is cosine, and cosine in absolute value is less or equal than 1. And same thing for cosine. Again, so this is more general than using trigonometric identities. Okay, so I will need these observations, these standard observations. So now I write f of xy in this form, and then I write f of x prime y prime. And I subtract the two. First component minus first component, second component minus second component. And I take absolute values. Now, if you look at first component, so 2 over 5 sine x minus 2 over 5 sine x prime plus 1 over 5 cosine y minus 1 over 5 cosine y prime, and same thing. You'll get 2 over 5, so this is an absolute value less than 2 over 5 x minus x prime, plus 1 over 5 x minus x prime, plus 1 over 5 y minus y prime, plus 3 over 5 y minus y prime, if you write this in details. Okay? So the 2 over 5, the first 2 over 5 comes from here, the second 2 over 5, the second 1 over 5 comes from here, and then 1 over 5, 3 over 5. So just take a paper and a pen and just subtract the 2. So this means that ρ1 of f of xy, f x prime y prime is less or equal than 2 over 5 plus 1 over 5 x minus x prime in absolute value plus 1 over 5 plus 3 over 5 y minus y prime. And this gives you 3 over 5 x minus x prime plus 4 over 5 y minus y prime in absolute value. And this is less, the 3 over 5 is less than 4 over 5. So this is less than 4 over 5 times the distance between xy and x prime y prime. And this means that f is a contraction of ratio 4 over 5, because 4 over 5 is less than 1. Okay, so what do we have? We have a contraction from R2 to itself, and R2 is complete with this distance ρ1. So we can apply the Banach fixed point theorem. Okay, so f maps R2 into itself. So according to the Banach fixed point theorem, f has a unique fixed point. We can call it x0, y0. Now, what is the relation with the second, with the system? If we divide by 5, the system would be equivalent to saying that f of xy equal xy. So xy is a fixed point. So the system, this nonlinear system, is equivalent to saying that xy is a fixed point of f. Okay, since f has a unique fixed point, then the system has a unique solution. And that's it. So this concludes exercise 3. Exercise 4, also an exercise on the fixed point theorem. So we consider the space X of positive numbers, and we equip it with this distance, dxy equal len x minus len y. Then you have to show that d is a distance and x is complete under this distance. And then we have to apply the Banach fixed point theorem. We consider a differentiable function from x to itself, so from the positive numbers to itself, satisfying this inequality. T, absolute value of f prime of t, is less or equal than a constant times f of t for all t in x, and for some constant k less than 1. You have to give an example of such function, and then you have to show that f has a unique fixed point by considering the auxiliary function g of t equal len of f of et. First question, I will not do it. You must be able to do it. It's straightforward. 4 properties of the distance. Now, yxd is complete. The strategy is standard. We start with an arbitrary Cauchy sequence, okay? And we prove that it's convergent for this distance. So what does it mean that it's a Cauchy sequence? It means that dxn xm can be made less than arbitrary small. So for every epsilon positive, starting from a certain rank, len of xn minus len of xm is less than epsilon. And this means that the sequence of real numbers, len of xn, is a Cauchy sequence in R equipped with the usual distance. Now we cannot call it d because we already took d. You can call it d prime if you like, or d bar. Okay, it's not a big deal. But since R is complete with respect to the usual distance, this means that len of xn converges in the usual sense to some limit y. Okay, if len of xn converges to y in the usual sense, then, and we take the exponential, then the exponential of len xn converges to the exponential of ey, okay, because the exponential is continuous. So if you put x equal ey, then necessarily x is positive, so x is in the space, capital X, and of course y equal len of x. Okay, therefore, since len of xn converges to y, then len of xn converges to len of x in the usual distance, and this means that the distance between xn and x converges to 0 in the usual sense, and therefore xn converges to x in xt. Okay, so this concludes B. Now the last question. It's enough to give an example of one function satisfying this inequality. So what if you just consider equality and assume that f and f prime are positive? So then it's enough to solve this differential equation, tf prime t equal kft. But this is a standard differential equation, linear differential equation. So how do you solve it? You divide by tft and you integrate. And then you should get f of t equal alpha times t to the k. And since f is positive, then alpha must be positive. Okay, so we have actually a family of such maps that satisfy the inequality. You may try to find other less trivial solutions. Now, why f has a fixed point? So we do as in the hint. We introduce g of t equal len of f of t. So g is differentiable, and by the chain rule, g prime of t equal f prime of et times et over f of et. And when I take the absolute value using the inequality, so if I put x equal et, then this is just f prime x times x over f of x. So it's less than k. So by the mean value theorem, g is a contraction actually. Okay, so it's Lipschitz continuous with a constant k. So in particular, if I put t equal len of x and s equal len of y for xy positive, I get len of x, len of fx, okay, minus len of fy is less than or equal to k, len x minus len y. And this means that the distance d between f of x and f of y is less or equal than k dxy. So this means that f is a contraction on xd. So since xd is complete and f is a self map, then f has a unique fixed point. Yeah. Now there's another way of proving this inequality, is to go back to this inequality, tf prime t less than kft in absolute value, okay, divide by tft and integrate. So of course we distinguish between three cases. If x equal to y, then both terms are 0, there's nothing to prove. If y is less than x, we write the integral from y to x of f prime of t, there's a parenthesis here, f prime over f. The antiderivative of f prime over f is ln of f, okay, evaluated between x and y. Okay, so this is the fundamental theorem of calculus. But now the absolute value of the integral is less than the integral of the absolute value. But the inequality f prime over f in absolute value is less than k over t. So this integral is less or equal than the integral from y to x of k over t, and you can compute this. This is just k ln x minus ln y, if y is less than x. Now, of course, it's less than the absolute value. If x is less than y, we can interchange the roles of x and y in this inequality, and then we get ln of fy minus ln of fx is less than k ln of y minus ln x. So therefore, in all cases, we have the inequality. Okay, so this concludes exercise 4 and the first part and this video as well. The next video, I'm going to solve the remaining exercises. So thank you for your attention.